Welcome to Evidence Mastery with Dr. Massoud Toussi. Let's dive right into this explainer on data linkage and integration. Whether you're a professional in pharma, healthcare, academia, a regulator, or a student, understanding exactly how we connect the dots in real-world data is absolutely essential. Today, we're going to explore how we take fragmented, messy records and transform them into comprehensive, meaningful patient narratives. I want you to imagine a patient's healthcare journey as, well, a shattered mirror. The pieces are just scattered everywhere, right? You've got pieces at primary care clinics, hospital discharge summaries, pharmacy dispensing logs, insurance claims, and specialized disease registries, because real-world data almost never exists in a perfectly curated single silo. Data linkage is really the art and science of putting those mirror pieces back together to reflect a complete longitudinal view of a patient's health. So, here is our roadmap for today's explainer. We'll start with the core problem of data fragmentation, and then walk through the exact methods we use to actually solve it, from deterministic and probabilistic linkage all the way to modern privacy-preserving techniques. We're also going to cover the cutting edge of multi-omics and, crucially, how to handle linkage bias. Okay, let's jump into Section 1, the RWD fragmentation problem, and how we reconstruct the patient journey. Moving right along to Section 2, deterministic data linkage, which is really all about the power of exact matching. When we successfully connect disparate data sources, we literally multiply the value of individual datasets. It's a real game changer. So let's dive into our first and honestly most straightforward method to achieve this, which is deterministic linkage. This operates on the very simple principle of exact matching. If a specific identifier in dataset A perfectly matches the same identifier in dataset B, boom, the records are assumed to belong to the exact same individual. Now, this relies heavily on having robust, unique identifiers. We're talking about things like a social security number in the US, a national health service number in the UK, or even study-specific trial IDs. Now, the primary strength of deterministic linkage is its simplicity. It's totally transparent, easily audited by clinical researchers and regulators, and it boasts incredibly high precision. But, and this is a big but, its major limitation is that it's highly fragile. It is incredibly susceptible to typos and formatting issues. For example, if an SSN is recorded with hyphens in one system and without hyphens in another, it will completely fail an exact string match unless you pre-process it. And obviously, if that unique identifier is just missing in even one dataset, the record simply cannot be linked. A really canonical example of doing this right is the SEER Medicare database in the United States. The National Cancer Institute links the SEER population-based cancer registry to Medicare claims deterministically. By using the patient's health insurance claim number along with their social security number, they achieve an exceptional linkage rate that historically exceeds 93%. Since Medicare enrollment actually requires an SSN and SEER actively collects it, this perfect exact match minimizes linkage error and has honestly been foundational to thousands of studies on cancer outcomes. Which brings us to Section 3, probabilistic data linkage, or as I like to think of it, embracing messy data. So what happens when those unique identifiers are missing, incomplete, or just totally unreliable? That is when we turn to probabilistic methods. This approach just accepts the reality that real-world data is, frankly, pretty messy. Instead of demanding a perfect, exact match, probabilistic linkage uses statistical models to weigh the evidence of a match across multiple non-unique fields. Think things like a patient's first name, their date of birth, and their zip code. The whole theoretical foundation for this goes back to the 1969 Falegi Center model, which basically treats record linkage as a hypothesis testing problem. We calculate two key probabilities for each field. First, the M probability, which is the likelihood of agreement if it's a true match. And second, the U probability, which is the likelihood of agreement by pure random chance for a non-match. So highly discriminatory fields like a full date of birth are going to yield very high positive match weights when they agree. But a super common first name like John, that yields a much, much lower weight. But here's the catch. If we try to compare every single record in dataset A against every single record in dataset B, the computational burden would be impossible. It would literally crash most systems. So we use a clever technique called blocking. We divide these massive datasets into smaller, manageable subsets based on reliable fields. For instance, we might tell the system to only compare records that have the exact same birth year and the same first letter of the last name. This drastically reduces the computational load while still capturing the vast majority of true matches. And here is a brilliant illustration of the payoff. The U.S. National Center for Health Statistics actually links the National Health Interview Survey to the National Death Index. Now, because the survey doesn't collect Social Security numbers for privacy reasons, they absolutely have to use probabilistic linkage based on fields like first name, last name, date of birth, sex, and state of residence. By setting rigorous probabilistic thresholds based on those flaky sooner weights we talked about, they achieve over 90% sensitivity for deceased individuals. This allows for incredibly vital longitudinal mortality research without ever needing a single unique identifier.
All right, let's move into Section 4, Privacy-Preserving Record Linkage, commonly known as PPRL.
Because of strict and very necessary regulations like GDPR in Europe and HIPAA in the US, sharing raw, identifiable data is often illegal and highly complex. Privacy-preserving record linkage allows researchers to connect the dots across different organizations without ever exposing the underlying, raw, personally identifiable information to any single party. The process behind this is absolutely fascinating. First, data custodians at the different sites clean and standardize their data completely independently. Then, they apply a cryptographic hash. This is a one-way mathematical function, like SHA-256, combined with a secret random string of characters called a salt. This turns a regular name or date of birth into a fixed-length string of secure, meaningless characters. The linkage engine only ever sees and matches these hashed tokens, never the original raw data.
But wait, hashing demands exact matches, right? So how do we handle typos in a privacy-preserving scenario? Well, researchers use incredibly advanced structures like Bloom filters. A Bloom filter breaks down a name into smaller pieces called n-grams and represents them as a bit array. This actually allows the linkage engine to calculate similarity scores completely blindly using secure multi-party computation. No single party ever sees the raw data, but they can still probabilistically link the records. It's genius.
For a globally recognized example of this executed flawlessly, look no further than the Sale Databank in Wales. They link population-scale health and social care data using an anonymizing third party, the NHS Wales Informatics Service. Data providers send pseudonymized records, demographic identifiers are processed totally separately from clinical data, and only a de-identified study-specific linkage key is returned to the researcher. The whole shebang works without anyone ever holding the complete identifiable record.
Let's push the envelope a bit in Section 5, Multi-omics and Imaging Linkage Challenges. We're moving to the cutting edge now, looking at how this all builds when we introduce high-dimensional biological and radiological data into the mix. Integrating multi-omics, like genomics and proteomics, with clinical electronic health records creates some massive structural hurdles. First up is temporal misalignment. A patient's EHR might contain daily vital signs, right? But their whole genome scan is a once-in-a-lifetime event. If we only link by broad annual timestamps, we lose the crucial sequence of cause and effect. Second, specialized biobanks or imaging systems often use totally different identifier schemas than hospital systems, which requires a highly robust crosswalk to map them accurately.
And then we have to consider the massive computational scale. To put this into perspective, while an EHR might take up just a few megabytes of space, a single whole genome sequence can easily exceed 100 gigabytes. It's a staggering volume disparity. A premier example of overcoming this is the UK Biobank, which masterfully tackles this for 500,000 participants. They provide a unified, cloud-based data environment where linkage keys are pre-resolved. This allows researchers to query the lightweight clinical metadata first and only pull those heavy petabyte-scale imaging or genomic files for their specific filtered cohort.
Finally, we must talk about Section 6, Linkage Bias and Error Propagation.
We really need to confront the reality that data linkage isn't just an administrative IT task. It is a methodological intervention with incredibly high stakes, fully capable of altering your study results. Because errors propagate directly into your analytics. False positives, or overlinkage, erroneously merge records of different people. This can artificially inflate comorbidities or create entirely false toxicity signals in pharmacovigilance. On the flip side, false negatives, or underlinkage, fail to connect records that genuinely belong together, fragmenting patient histories. If a patient's death record fails to link to their EHR, they might be treated in the data as simply lost to follow-up, which can severely overestimate survival rates.
And from a methodological standpoint, we have to note that this linkage bias isn't always evenly distributed. A truly crucial 2016 study by Heron and colleagues demonstrated differential linkage bias in perinatal research when linking hospital maternity records. The analytics revealed something alarming. Unlinked records disproportionately belong to mothers who are younger, of non-white ethnic backgrounds, or living in deprived neighborhoods. If researchers don't assess and report linkage quality by demographic subgroup, the data itself can systematically underrepresent specific vulnerable populations. It's a technical flaw that actively masks health inequalities and requires transparent reporting and sensitivity analyses to ensure data integrity.
So, what does this all mean for us? The ultimate question is, how will you ensure your data linkage reveals the truth instead of accidentally hiding it? By the way, all of this content is taken directly from my book, Real-World Evidence, Sources and Solutions, which will become available this year. Please make sure to subscribe to my channel to see many more explainers diving into the fascinating world of real-world evidence and real-world data. Thank you so much for joining me, and I'll catch you in the next explainer.